If you wish to look back to the very dawn of creation, you do not look up at the stars. You look down. Deep beneath the tranquil borders of France and Switzerland, buried 300 feet beneath the quiet meadows and cobblestone streets, lies a sleeping leviathan. It is the most complex machine ever constructed by human hands, a cathedral of modern science, a 27-kilometer ring of superconducting steel and wire that defies the limits of human engineering. This is the Large Hadron Collider, or the LHC. Built by CERN, the European Organization for Nuclear Research, it is not simply a laboratory. It is humanity's greatest time machine. Its singular purpose, to forcefully rip away the veil of reality and plunge us back to a time when the universe was less than a billionth of a second old. But to touch the fires of creation, humanity first had to engineer the coldest place in the known universe. To control the chaotic subatomic storms raging inside this machine, the LHC's 17-mile tunnel is wrapped in a sophisticated cryogenic cooling system. Liquid helium pumps relentlessly through the veins of the collider, bringing the temperature of the massive superconducting magnets down to minus 271 degrees Celsius or 1.9 Kelvin. To put that into perspective, the empty void of interstellar space, far from the warmth of any star, sits at around 2.7 Kelvin. The inside of the LHC is literally colder than outer space. It is an artificial pocket of absolute stillness designed to ensure that the electrical currents powering the electromagnets flow without a single fraction of resistance. Within this freezing void, the true violence begins. The LHC is a track meant for the ultimate cosmic race. Scientists extract protons, the positively charged building blocks of atomic nuclei, from a simple bottle of hydrogen gas. These tiny specks of matter are injected into two ultra-high vacuum pipes running parallel to each other. One beam travels clockwise, the other counterclockwise. Then the magnets awaken. Over 9,000 superconducting magnets, some weighing up to 35 tons each, act as an invisible magnetic whip. They steer and accelerate these microscopic chariots faster and faster around the 27-kilometer track. The protons are pushed to the absolute breaking point of physics. They accelerate until they are traveling at 99.9999991% the speed of light. At this velocity, a single proton loops the entire 17-mile underground ring over 11,200 times every single second. They are moving so fast that time itself begins to warp and dilate around them, exactly as Albert Einstein predicted. But they are not meant to run forever. They are meant to crush. At 4 precisely engineered intersection points around the ring, the beams are forced to cross. 40 million times every second, packets of protons slam into one another in head-on collisions. When these particles crash at near light speed, they do not just bounce off each other, they shatter. The kinetic energy of their impact is so terrifyingly dense that for a fleeting fraction of a microsecond, the temperature at the collision point spikes to over 100,000 times hotter than the core of the Sun. In that microscopic inferno, the fundamental laws of nature break down. Under normal conditions, quarks, the tiny subatomic particles that make up protons, are permanently locked together by gluons, the carrier particles of the strong nuclear force. They are trapped in an eternal unbreakable prison, but at temperatures of trillions of degrees, the prison melts. The protons melt. For the briefest instant, the quarks and gluons are ripped apart, roaming freely in an exotic state of matter known as the quark-gluon plasma. This is not a solid, a liquid, or a gas. It is a perfect fluid, a primordial soup of pure, unadulterated energy that flows with almost zero friction. This perfect fluid has not existed in our universe for 13.8 billion years. The last time this chaotic, beautiful plasma flowed freely, the universe was only a millionth of a second old. By colliding particles in the freezing depths of Geneva, humanity is quite literally holding the Big Bang in the palm of its hand. We are summoning the ghosts of creation to answer our most desperate questions. For decades, we thought we knew exactly what those ghosts would tell us. We had a map, a flawless mathematical blueprint of reality that explained everything we saw in the debris of these collisions. But as the LHC pushed further into the unknown, the whispers from the Big Bang began to change, and humanity's perfect map was about to catch fire. For 50 years, humanity constructed a fortress of pure thought. We called it the Standard Model of Particle Physics. It was not merely a theory, it was an empire, an unparalleled triumph of human intellect that successfully explained almost everything we could see, touch, and measure in the known universe. To understand the sheer magnitude of the crisis that is currently unfolding in modern physics, you must first understand how absolute and impenetrable this mathematical fortress appeared to be. The Standard Model was born in the latter half of the 20th century, pieced together by the brightest minds across generations. It reduced the infinite complexity of the cosmos into a beautifully simple and terrifyingly precise recipe. Imagine a vast cosmic periodic table, but instead of chemical elements, it catalogues the absolute smallest fragments of reality. According to the Standard Model, everything in existence is constructed from just 12 fundamental particles of matter and governed by 3 fundamental forces. The matter particles are divided into 2 distinct families, quarks and leptons. Quarks are the sociable builders. They bind together to form protons and neutrons, creating the heavy hearts of atoms. Leptons, on the other hand, include the familiar electron, which buzzes around the atomic nucleus, bringing electricity, chemistry, and life itself into existence. But particles alone cannot build a universe. They need rules. They need forces to tell them how to move, how to bind, and how to decay. The Standard Model identifies these forces and assigns them messenger particles known as bosons, which carry instructions between the matter particles. The strong nuclear force carried by gluons operates like cosmic glue, holding the nucleus of an atom together against immense repulsive pressures. The electromagnetic force carried by photons governs light, electricity, and the magnetic fields that shield our planet. The weak nuclear force carried by the W and Z bosons orchestrates the slow, silent alchemy of radioactive decay and fuels the nuclear fusion burning in the core of our sun. For decades, the predictions made by this mathematical framework were tested in laboratories and particle accelerators around the world. And every single time the Standard Model emerged victorious, it predicted the existence of quarks before we ever saw them. It predicted the masses of the W and Z bosons with astonishing accuracy. It was a flawless map of the quantum realm. But for a long time, there was a glaring, haunting, empty space on this map. The equations of the Standard Model worked perfectly, except for one massive contradiction. According to the raw mathematics, none of these particles should have any mass. They should all be zipping through the universe at the speed of light, meaning atoms could never form, stars could never ignite, and you and I could never exist. To fix this catastrophic flaw, physicist Peter Higgs and his colleagues proposed a radical idea in the 1960s. They theorized an invisible universe-spanning field that drags on certain particles, giving them mass. The signature of this field would be a new particle, the Higgs boson. Finding the Higgs boson became the holy grail of modern science. It was the ultimate test. If the Higgs did not exist, the entire Standard Model would collapse, taking 50 years of physics down with it. That is precisely why the Large Hadron Collider was built. And on July 4, 2012, the world watched in awe as CERN made the most monumental announcement in the history of particle physics. Deep in the data of trillions of collisions, they had found it. The Higgs boson was real. The final piece of the puzzle had been locked into place. The Standard Model was complete. The scientific community erupted in celebration, and Nobel Prizes were rightfully awarded. But what exactly does it take for physicists to claim a discovery? They do not rely on hunches or single anomalies. The empire of the Standard Model demands a level of proof that borders on the impossible. In the realm of particle physics, a discovery must reach a statistical threshold known as 5 sigma. To put it simply, 5 sigma means that if the particle did not actually exist, there is only a 1 in 3.5 million chance that the experimental data could have spiked in such a way purely by a random fluke. When we talk about a 1 in 3.5 million chance of being wrong, we are talking about a standard of evidence that exists nowhere else in science. In biology, a 1 in 20 chance of error is often considered significant. In medicine, a 1 in 1,000 chance of a false positive is highly rigorous. But fundamental physics demands perfection. It demands that the universe repeats its secrets over and over again across billions of collision events until every shadow of a doubt is eradicated by pure blinding statistical light. It is a gold standard of absolute certainty. The Higgs boson cleared the 5 sigma hurdle, solidifying the Standard Model as the most successful scientific theory ever devised by humankind. I always thought the discovery of the Higgs boson was the ultimate victory, the final chapter in the book of fundamental physics. But in reality, it was not the end. It was the quiet, serene moment right before a massive storm. With the Higgs confirmed the map was finished, physicists expected the Large Hadron Collider to simply confirm what they already knew, to add a few decimal places of precision to a completed masterpiece. Instead, as the machine ran at higher energies and collected unprecedented mountains of data, the universe began to whisper something deeply unsettling. The numbers began to drift. At first, they were just tiny whispers in the background noise. A fraction of a percent here, a slight deviation there. Nothing close to a 5 sigma discovery, just isolated ghosts in the machine. But then the ghosts started to multiply. The data pouring out of the Large Hadron Collider and soon from other accelerators across the Atlantic began to stubbornly refuse to align with the sacred equations of the Standard Model. Particles were decaying incorrectly. They were wobbling at the wrong frequencies. They were weighing more than they physically should. The flawless fortress that had stood undefeated for half a century was suddenly showing profound, undeniable cracks. The scientific community realized, with a mix of dread and absolute exhilaration, that they were standing on the edge of an abyss. The Standard Model was not the absolute truth of the universe. It was just a thin local illusion hiding a much deeper, chaotic, and completely unknown layer of reality. And the first true alarm bell, the anomaly that forced the world to finally admit that our understanding of physics was broken, came from one of the most unstable and short-lived fragments of matter ever studied. The first true fracture in the absolute authority of the Standard Model did not come from a blinding, world-shattering collision. It came from the quiet, meticulous observation of one of the most unstable and elusive fragments of matter in the universe. Deep within the Large Hadron Collider ring sits an experiment known as LHCb. Unlike the massive barrel-shaped detectors that look for head-on impacts, LHCb is designed specifically to capture the debris that flies forward along the beamline. Its primary mission is to study a very specific, incredibly strange particle known as the beauty quark. In the sterile language of physics, it is officially called the bottom quark, but scientists often prefer the term beauty because it offers a perfect window into the hidden symmetries of the cosmos. The beauty quark is exceptionally heavy, roughly 4 times the mass of a proton, and because of this immense mass, it is violently unstable. The moment it is created in the fiery aftermath of a proton collision, it exists for only a fraction of a trillionth of a second before decaying, shattering into a cascade of lighter, more stable particles. But it is precisely within this microscopic window of decay that the secrets of new physics can hide. According to quantum mechanics, when a heavy particle decays, it does not just split apart like a cracked stone. It morphs, transitioning through intermediate states, often summoning virtual particles from the quantum vacuum for fleeting instants before vanishing back into nothingness. If there are undiscovered forces or unseen particles hiding in the dark sectors of the universe, their quantum influence would subtly alter the way the beauty quark breaks apart, leaving a mathematical fingerprint in the wreckage. The scientists at LHCb were not looking for a new particle directly, they were looking for a shadow. They were measuring a foundational principle of the Standard Model known as lepton universality. To understand this profound principle, you must understand the strange family of particles known as leptons. The most famous lepton is the electron, the tiny negatively charged particle that powers our civilization, creates chemical bonds, and forms the outer shell of every atom in your body. But the electron has a heavier sibling, a particle called the muon. A muon is completely identical to an electron in every single conceivable way. It has the exact same negative electric charge. It has the exact same quantum mechanical spin. The only difference in the entire universe is that the muon is roughly 207 times heavier than the electron. Under the strict unyielding laws of the Standard Model, the fundamental forces of the universe are completely blind to mass when determining how particles interact. The weak nuclear force and the electromagnetic force should interact with an electron exactly the same way they interact with a muon. They are treated as mathematical equals. Therefore, when a beauty quark decays and its energy transforms to produce these leptons, the laws of physics dictate a strict, unbreakable symmetry. The beauty quark should decay into electrons at the exact same rate that it decays into muons. The ratio must be a perfect unyielding 1-to-1. This is lepton universality. It is a central pillar of modern physics, a profound mathematical statement that the fundamental forces of the universe do not play favorites. For years, the LHCb detector meticulously counted these microscopic shattering events, 1 million, 10 million, 100 million decays. But as the data poured in and the supercomputers crunched the numbers, a terrifying pattern began to emerge from the background static. The universe was playing favorites. The data showed that the beauty quarks were not decaying equally. They were decaying into electrons significantly more often than they were decaying into muons. At first, the researchers assumed it was an error, a glitch in the detector, a misaligned sensor, a flaw in the incredibly complex algorithms used to filter the background noise. They spent years agonizing over the data, recalibrating, retesting, trying desperately to find the mistake that would restore order to the Standard Model. But the anomaly refused to vanish. In fact, as they collected more data, the discrepancy only grew sharper and more defined. The statistical significance breached the 3 sigma mark, meaning there was only about a 1 in 1,000 chance that this was a random statistical fluctuation. While not yet the gold standard of a 5 sigma discovery, it was a blaring siren in the dark. Something invisible, something completely unwritten in the textbooks of physics, was reaching out from the quantum vacuum and interfering with the decay. It was putting its invisible thumb on the cosmic scale, actively hindering the creation of muons or actively promoting the creation of electrons. If this data holds true, the implications are absolutely staggering. It means that our understanding of the fundamental forces is fundamentally flawed. It implies the existence of a brand new 5th fundamental force of nature, carried by a particle humanity has never seen. Theoretical physicists immediately began drafting blueprints for what this entity could be. Some proposed a heavy exotic particle called a Z-prime boson, a darker, heavier cousin of the particles that carry the weak nuclear force. This hypothetical force carrier would have a bizarre preference for interacting with different generations of leptons, explaining the unequal decay. Others suggested something even more radical, a leptoquark. A leptoquark is an unprecedented bridge particle that would allow quarks and leptons to directly interact and transform into one another. The existence of such a particle would completely shatter the rigid classification barriers that have defined particle physics for a century, merging the 2 fundamental families of matter into a single unified framework. The beauty quark anomaly was no longer just a mathematical curiosity buried in a hard drive. It was a beacon signaling that a massive undiscovered continent of physics was waiting just beyond the horizon of our current technology. It proved that the Standard Model, for all its terrifying predictive power, was incomplete. It was blind to a force that was actively shaping the microscopic architecture of reality. But the most chilling realization was yet to come. Because as the scientists in Europe wrestled with the strange behavior of the beauty quark, another team of physicists, thousands of miles away across the Atlantic Ocean, were about to detonate a bombshell of their own. They were looking at the very same particle, the muon, but in a completely different way. And what they found would not just crack the standard model, it threatened to tear the entire fortress down to its very foundations. While the scientific community was grappling with the unsettling data emerging from the Large Hadron Collider in Europe, another storm was quietly brewing across the Atlantic Ocean. To prove that the strange behavior of the quantum realm was not merely an isolated glitch within a single machine, scientists needed independent verification. They needed to test the fundamental laws of nature using a completely different method, a completely different machine, and a completely different particle. They turned their attention to the muon. To understand the gravity of what happened next, you must first understand what a muon actually is. As we established earlier, the muon is the heavier sibling of the electron. It is identical in its negative electric charge and its quantum spin, but it is roughly 200 times more massive. Unlike the stable electrons that power our modern world, muons are highly unstable. They do not naturally exist in the atomic structures around us. Instead, they are born in the violent upper layers of Earth's atmosphere. When high-energy cosmic rays from deep space slam into the atmospheric gases of our planet, they trigger a cascading shower of subatomic debris. This continuous cosmic bombardment creates muons that rain down on the surface of the Earth every single second. Right now, as you listen to this, dozens of invisible muons are passing through your body, traveling at nearly the speed of light, before decaying harmlessly into lighter particles. Because of their unique mass and quantum properties, muons act like incredibly sensitive cosmic antennas. According to quantum mechanics, particles are never truly alone. The empty space around them is not empty at all. It is a boiling, chaotic quantum vacuum, where virtual particles constantly pop into and out of existence for microscopic fractions of a second. As a muon travels through space, it interacts with this invisible quantum sea. It constantly absorbs and emits these fleeting virtual particles. If the standard model is completely accurate, we should know exactly which virtual particles the muon is interacting with because we know all the particles that exist. But if there are undiscovered particles hiding in the dark forces we have never seen, they too would emerge from the quantum vacuum and subtly pull on the muon. The ultimate test of this theory was designed at Fermilab, the premier particle physics laboratory in the United States, located just outside of Chicago, Illinois. But to execute this unprecedented experiment, scientists needed a very specific piece of equipment. They needed a massive, perfectly circular 50-foot wide superconducting electromagnet. The problem was that the only magnet capable of such extreme precision was located at the Brookhaven National Laboratory in New York, nearly 1,000 miles away. You cannot simply dismantle a highly sensitive 17-ton superconducting magnet. It had to be transported entirely intact without bending or warping even a fraction of a millimeter. In the summer of 2013, the massive ring was carefully loaded onto a specialized barge. It traveled down the east coast of the United States, around the tip of Florida, into the Gulf of Mexico, and then slowly navigated up the Mississippi, Illinois, and Des Plaines rivers. It was a logistical masterpiece, a giant futuristic metallic ring floating past the American heartland, all for the purpose of measuring a particle that exists for only 2/millionths of a second. Once safely installed at Fermilab, the experiment officially known as muon G-2 finally began. The concept was beautifully simple, yet terrifyingly complex in its execution. Like all fundamental particles with an electric charge and a quantum spin, the muon acts like a tiny microscopic compass needle. When you place a muon inside a powerful magnetic field, it does not just sit still. It spins, and as it spins, its internal magnetic axis wobbles much like a spinning top, wobbles as it slows down. This wobble is scientifically known as magnetic precession. The rate at which the muon wobbles is determined by a number called the G factor. For a completely isolated particle, the mathematics of the early 20th century predicted this number should be exactly 2. But because the muon is constantly interacting with the chaotic quantum vacuum, pulling in and pushing out virtual particles, its wobble is slightly altered. It is shifted by a microscopic fraction. This anomalous magnetic moment, the tiny deviation from the number 2, is what the experiment aimed to measure. Theoretical physicists had already calculated exactly what this wobble should be, factoring in every single known particle and force in the standard model. Their mathematical prediction was precise to an astonishing 12 decimal places. It was one of the most rigorously calculated numbers in the history of human knowledge. The Fermilab machine shot billions of muons into the perfectly uniform magnetic field of the giant ring. They watched the microscopic compass needles wobble, measuring their precession with a level of precision that is almost impossible to comprehend. For years, supercomputers analyzed the decay trajectories, filtering out the noise, narrowing down the margin of error. In April of 2021, the Fermilab team was finally ready to unveil their findings to a waiting, anxious scientific world. When the data was unblinded, the results sent a shockwave through the physics community. The moons were wobbling too fast. The measured magnetic moment did not match the immaculate predictions of the standard model. Something invisible, something massive and unknown was emerging from the quantum vacuum and pulling on the moons, causing them to precess faster than the laws of physics allowed. The discrepancy between the theoretical prediction and the experimental reality reached a statistical significance of 4.2 sigma. This meant there was only a 1 in 40,000 chance that this result was a mere statistical fluke. While not yet the 5 sigma gold standard, when combined with the glaring anomalies already detected in the beauty quark experiments over at the Large Hadron Collider, the picture became undeniably clear. The anomalies were not isolated, they were systemic. They were appearing in different particles in different machines on different continents. The Fermilab result was the devastating confirmation that the European scientists had been waiting for. The standard model was failing. The quantum sea was swarming with unseen ghosts, entirely new forces of nature or exotic particles that have eluded human detection for a century. The invisible architecture of the universe was finally revealing itself, and it was vastly more complex and more mysterious than anyone had dared to imagine. While the anomalies involving the beauty quark and the muon hinted at invisible forces operating on the fringes of the standard model, the next monumental fracture occurred directly at its structural core. To understand this paradigm-shifting event, we must turn our attention away from the exotic and look toward the force that literally powers the stars. Of the 4 fundamental forces of nature, the weak nuclear force is arguably the most counterintuitive. Unlike gravity, which pulls galaxies together, or electromagnetism, which binds atoms and creates light, the weak force does not push or pull in the traditional sense. Instead, it transforms. It operates as the ultimate cosmic alchemist, possessing the unique ability to reach inside the atomic nucleus and change the fundamental identity of subatomic particles. When a star like our Sun burns, it relies on the weak force to initiate nuclear fusion. The weak force triggers a process where a down quark inside a neutron flips into an up quark, transforming that neutron into a proton. This microscopic transmutation releases the boundless energy that bathes our planet in warmth and sustains all life on Earth. But fundamental forces do not act by magic. They require messengers to carry their instructions across the quantum void. For the weak force, one of these primary messengers is a particle known as the W boson. The W boson is a behemoth of the quantum world. It is astonishingly heavy, weighing nearly 80 times more than a standard proton. However, in the unforgiving realm of particle physics, extreme mass comes at a catastrophic cost to stability. The moment a W boson is summoned into existence, it is immediately crushed by its own weight. It survives for merely a fraction of a septillionth of a second before violently decaying into a lighter lepton, such as an electron or a muon, along with an invisible ghost particle called a neutrino. Because its lifespan is so incomprehensibly short, capturing and studying a W boson is one of the most agonizing challenges in modern science. You cannot isolate a W boson in a vacuum chamber. You cannot place it on a microscopic scale. The only way scientists can determine its mass is by studying the shattered debris it leaves behind after it decays, tracing the trajectories of the resulting electrons and muons outward to calculate the original energy of the particle that birthed them. This Herculean task was undertaken by the Collider detector at Fermilab, or the CDF collaboration utilizing the mighty Tevatron particle accelerator in Illinois. The researchers did not simply look at a few collisions. They embarked on an obsessive 4-decade-long campaign of data collection and analysis. They sifted through the wreckage of trillions of proton and antiproton collisions, meticulously isolating over 4 million individual W boson decay events. To measure the mass of this fleeting particle with any degree of accuracy requires an understanding of the experimental apparatus that borders on madness. The scientists had to account for the microscopic alignment of every sensor, the subtle fluctuations in the magnetic fields, and the precise behavior of millions of background particles that could distort the final measurement. To prevent any subconscious human bias from influencing the outcome, the researchers operated under a strict blinding protocol. The final mathematical offset was hidden from them for years, locked away in an encrypted file. They spent decades checking and rechecking their algorithms, calibrating their models against known particles, ensuring that their theoretical foundation was absolutely flawless. Finally, in the year 2022, the team agreed that they could do no more. The data was unblinded, the final algorithms were executed, and the measured mass of the W boson was revealed to the world. The standard model of particle physics, utilizing its rigid, perfectly balanced equations, predicted that the W boson should have a mass of exactly 80,357 mega-electron volts. But the Tevatron data told a different story. The CDF experiment measured the mass of the W boson at 80,433 mega-electron volts. It was heavier than predicted. The difference might seem incredibly small, less than 0.1%. In many fields of science, such a minor discrepancy would be rounded off and dismissed as an experimental artifact. But in the hyper-precise architecture of quantum physics, this tiny deviation is the equivalent of a catastrophic earthquake. The mathematics of the standard model are not isolated individual equations. They form a deeply entangled interconnected web known as electroweak theory. The mass of the W boson is mathematically locked into a strict relationship with the mass of the Higgs boson and the heaviest known particle, the top quark. If the W boson is heavier than the equations dictate, it means the entire mathematical framework holding the standard model together is out of balance. It implies that the theory we have relied upon for 50 years is fundamentally incomplete. More importantly, the statistical significance of this measurement was absolutely devastating. The deviation from the standard model reached 7 sigma. In the realm of particle physics, a 5 sigma result is enough to claim a definitive discovery and rewrite the textbooks. A 7 sigma result means there is less than a 1 in a trillion chance that this measurement is a random statistical fluke. It is one of the most precise and definitive anomalies ever recorded in the history of science. Just like the muon wobbling in its magnetic field, the unexpectedly heavy W boson suggests that unseen entities are lurking in the quantum vacuum. The current leading theory is that undiscovered, incredibly massive particles are popping into existence for brief moments, interacting with the W boson and lending it a phantom mass before vanishing back into the void. The standard model is completely blind to these interactions because it does not know these new particles exist. The W boson mass shock proved beyond a shadow of a doubt that the anomalies we are seeing are not isolated errors. They are the unmistakable signatures of a vastly more complex, unmapped universe. But as physicists scramble to identify these new forces and particles, they are also forced to confront an even deeper, more terrifying mystery. The cracks in the Standard Model are not just about particles behaving badly. They point toward a fundamental flaw in our understanding of why anything in the universe exists at all. To find the ultimate limits of our physics, we must leave the realm of the weak force and face the greatest paradox in the cosmos, the devastating war between matter and antimatter, and the impossible asymmetry that allowed humanity to be born. Every anomaly we have explored so far, from the bizarre decay of the beauty quark to the mysterious wobbling of the muon and the impossible weight of the W boson, points to invisible particles and undiscovered forces hiding in the dark. But while these anomalies threaten to break the mathematical equations of the Standard Model, there is a much deeper, far more terrifying flaw in our understanding of physics. It is a flaw so profound that it does not just question how particles interact. It questions why anything in the universe exists at all. To understand the ultimate failure of our current physics, we must leave behind the isolated collisions in Geneva and Illinois and journey back 13.8 billion years to the absolute beginning of time. According to the foundational laws of quantum mechanics and relativity, pure energy can be converted into physical matter. This is the very essence of Albert Einstein's famous equation E equals mc squared. In the blinding, unimaginable heat of the Big Bang, a singularity of infinite density exploded outward, releasing a shock wave of pure, unadulterated energy. As the primordial cosmos expanded and rapidly cooled, this boiling sea of energy began to condense into the first physical particles. But there is a strict, unbreakable, and terrifying rule governing the creation of matter. The universe demands absolute balance. Whenever energy transforms into matter, it must create two perfectly opposing entities simultaneously. For every particle of normal matter that is born, an exact twin of antimatter must also be created. Antimatter is not science fiction. It is a very real, mathematically necessary counterpart to the physical world we know. An antiparticle has the exact same mass as its normal counterpart, but it carries the opposite electrical charge and opposite quantum properties. For every negatively charged electron born in the fires of the Big Bang, a positively charged positron had to be created. For every quark and antiquark, in the first millionth of a second of creation, the universe was a violently balanced war zone filled with exactly 50% matter and exactly 50% antimatter. But this perfect symmetry carries a deadly consequence. When a particle of matter and a particle of antimatter touch, they completely destroy each other. They annihilate in a blinding flash of pure energy, leaving absolutely nothing behind but light. Therefore, if the laws of physics, as we understand them, are absolute, the early universe should have been a very brief, spectacular suicide. The equal oceans of matter and antimatter should have crashed into one another, continuously annihilating until every single particle in existence was destroyed. The cosmos should have been left as a vast, expanding and completely empty void, filled with nothing but cold, ancient light. No atoms should have survived. No stars should have ignited. No galaxies should have formed. And you and I should absolutely not exist. But we do exist. You are here watching this made of solid, stable matter. The earth beneath your feet, the sun in our sky, and the billions of galaxies stretching across the observable universe are all made exclusively of normal matter. Antimatter, for all intents and purposes, has completely vanished from the cosmos. It only appears fleetingly during violent cosmic ray collisions or deep inside our particle accelerators before being instantly destroyed. The fact that you are alive right now proves that something went catastrophically wrong with the perfect balance of the universe. In the epic war between matter and antimatter, matter somehow won. But how did we survive the Great Annihilation? In 1964, two physicists named James Cronin and Val Fitch conducted an experiment that shocked the scientific world and earned them the Nobel Prize. They discovered a microscopic flaw in the mirror of the universe, a phenomenon known as charge parity violation or CP violation. Until that moment, physicists believed that if you took a particle, swapped its charge to make it antimatter, and flipped its spatial coordinates, like looking in a mirror, the fundamental laws of physics would treat it exactly the same. But Cronin and Fitch discovered that the weak nuclear force, the same force that governs the heavy W boson we discussed earlier, occasionally breaks this rule. It does not treat matter and antimatter perfectly equally. There is a microscopic asymmetry during the chaotic boiling aftermath of the Big Bang, as matter and antimatter were locked in their apocalyptic war of annihilation. This tiny CP violation tipped the scales. For every 1 billion particles of antimatter that were created, there were 1,000,000,001 particles of normal matter. It was a discrepancy so incredibly small that it almost defies comprehension. 1 extra particle of matter for every billion pairs that annihilated each other. To understand the scale of this imbalance, imagine a cosmic scale holding 1 billion grains of sand on the left representing antimatter and 1,000,001 grains of sand on the right representing normal matter. When the annihilation occurred, it swept away 1 billion grains from both sides. The entire visible universe, every single galaxy, every nebula, every black hole, and every human being that has ever lived is constructed entirely from that single surviving grain of sand. As the universe expanded and cooled, the great annihilation raged until all the antimatter was completely eradicated. The vast, overwhelming majority of normal matter was destroyed right along with it. But because of that tiny 1 in a billion asymmetry, a small fraction of normal matter was left over. The ashes of that cosmic war, the survivors of the annihilation, went on to build every single star, planet, and biological organism in the universe today. We are the microscopic remainder of a nearly perfect cosmic suicide. The discovery of CP violation was a monumental triumph, and scientists eventually managed to incorporate it into the equations of the Standard Model by studying the decay of neutral subatomic particles that were observed changing their identities. But here is where the fortress of modern physics completely collapses. When we use the Standard Model to calculate the exact amount of CP violation that the weak force can generate, the number we get is devastatingly small. The math tells us that the asymmetry built into our current laws of physics is billions of times too weak to account for the survival of the universe. If the Standard Model is the absolute truth, the tiny imbalance it provides would not have been enough to save us. Matter and antimatter would have annihilated almost completely, leaving a universe with perhaps 1 stray proton every few million light years. The fact that entire galaxies exist is glaring, undeniable proof that the Standard Model is missing a massive piece of the puzzle. There must be an undiscovered, incredibly powerful source of CP violation hiding somewhere in the dark sectors of the universe. There must be unknown particles, perhaps heavy exotic particles, yet to be theorized or completely unmapped, fundamental forces that heavily favored the creation of normal matter in the first fraction of a second of time. We are living, breathing anomalies. Our very existence is a direct violation of the physics we currently understand. The ghosts we are chasing in our particle colliders are not just mathematical curiosities. They are the invisible architects that saved us from total cosmic erasure. But as we look out into the vastness of space to find answers, we encounter an even more terrifying reality. The Standard Model doesn't just fail to explain why matter survived. It fails to explain the behavior of the cosmos on the largest scales imaginable. Because when we step back and look at the galaxies spinning in the dark, we realize that the matter that makes up you, me, and the stars is entirely insignificant compared to the invisible monsters that truly rule the universe. For all the microscopic anomalies we have hunted down inside our underground colliders, the most glaring, undeniable failure of the Standard Model is not found by smashing particles together. It is found by simply stepping outside on a clear night and looking up at the stars. The Standard Model is a breathtakingly precise mathematical architecture that perfectly unites three of the fundamental forces of nature. It explains the electromagnetism that lights our cities, the strong nuclear force that binds the cores of atoms, and the weak nuclear force that dictates radioactive decay. But there is a fourth force. It is the very first force humanity ever recognized. The force that keeps our feet anchored to the ground, shapes the orbits of planets, and crushes dying stars into black holes. It is gravity. And yet if you look at the master equations of the Standard Model, gravity is completely absent. It simply does not exist. Our understanding of gravity is governed by an entirely different framework, Albert Einstein's theory of general relativity. General relativity describes gravity not as a particle but as the warping and curving of the very fabric of space and time. It works flawlessly on massive cosmic scales. But when physicists try to shrink general relativity down to the microscopic quantum realm, the mathematics utterly collapse. The equations spit out infinities and impossibilities. For nearly a century, the greatest minds in physics have tried to unite the quantum forces of the Standard Model with the gravitational forces of general relativity to create a single unified theory of everything. And for nearly a century they have failed. The Standard Model is entirely blind to gravity. And because it is blind to gravity, it is completely blind to the true rulers of the cosmos. To understand the sheer scale of our ignorance, we only need to look at the spinning disks of distant galaxies. In the 1970s, astronomer Vera Rubin was studying the rotation rates of spiral galaxies, mapping how fast the stars at the outer edges were moving compared to the stars near the galactic core. According to the laws of classical physics, a galaxy is much like our solar system. The planets furthest from the Sun move slower than the planets close to it because the gravitational pull weakens with distance. Therefore, the stars at the outer edges of a galaxy should be orbiting much slower than the stars trapped in the dense luminous core. But that is not what the telescopes revealed. Rubin discovered that the stars at the outer edges were tearing through space at impossible velocities. They were moving so incredibly fast that the visible mass of the galaxy, all the glowing stars, gas clouds, and dust, did not possess anywhere near enough gravitational pull to keep them in orbit. By all known laws of physics, these galaxies should have ripped themselves apart, violently flinging their stars out into the freezing void of intergalactic space. The only logical explanation was that the galaxies were embedded in a massive invisible halo of some unknown material. A material that does not absorb light, does not reflect light, and does not interact with electromagnetism in any way. It only interacts through the sheer brute force of gravity. We call this phantom material dark matter. When astronomers calculated the immense gravitational pull required to hold the spinning galaxies together, the numbers were staggering. Dark matter does not just exist, it completely dominates the cosmos. It outweighs the visible matter in the universe by a ratio of more than 5-to-1. So the astronomers turned to the particle physicists and asked a simple question: which particle in the Standard Model accounts for all this invisible mass? The particle physicists checked their flawless 50-year-old map of reality and found absolutely nothing. Not a single particle in the Standard Model possesses the necessary properties to be dark matter. It is a complete unknown. The matter that makes up you, me, the Earth, and every single star you can see in the night sky accounts for a mere 5% of the total mass energy budget of the universe. The Standard Model is not a theory of everything. It is a theory of the 5%. We are adrift in a vast dark ocean and we only have a map of the foam on the surface. But the nightmare for modern physics does not end with dark matter. In the late 1990s, astronomers were studying the light from distant exploding stars known as Type 1a supernovas. They were trying to measure how quickly the gravitational pull of all the matter in the universe was slowing down the cosmic expansion that began with the Big Bang. They expected to find that the expansion of the universe was gradually decelerating, exhausted by the relentless inward pull of gravity. Instead, they discovered the exact opposite. The expansion of the universe was not slowing down, it was accelerating. Some mysterious repulsive force was actively pushing the fabric of space-time apart, driving the galaxies away from each other at ever-increasing speeds. We call this terrifying anti-gravitational force dark energy. It is the dominant force in the cosmos, making up roughly 68% of the universe. To explain dark energy, quantum physicists turned to the concept of vacuum energy, the inherent boiling energy of empty space created by the constant popping in and out of virtual particles. They used the absolute best mathematics the Standard Model had to offer to calculate how much vacuum energy should exist in the universe and compared it to the amount of dark energy the astronomers were actually observing. The result was the most humiliating failure in the history of science. The quantum prediction was larger than the astronomical observation by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is a discrepancy so unfathomably massive that there are not enough atoms in the universe to write the number out physically. It is undeniably the worst prediction ever made by theoretical physics. The accelerating expansion of the universe, the existence of dark energy, and the overwhelming presence of dark matter prove that our fundamental understanding of reality is deeply structurally broken. The anomalies we are seeing in our underground colliders, the wobbling muons and the heavy W bosons, are not just isolated glitches. They are the tiny microscopic ripples of these massive invisible cosmic forces finally bleeding into our human instruments. The ghosts of the universe are finally making themselves known, and to capture them, physicists are being forced to propose theoretical particles and dimensions that sound less like science and more like pure science fiction. For half a century, the laws of physics dictated that every interaction in the known universe, from the majestic orbit of galaxies to the microscopic decay of a radioactive atom, was governed by just 4 fundamental forces: gravity, electromagnetism, the strong nuclear force and the weak nuclear force formed the absolute bedrock of our reality. They were the 4 pillars holding up the entire architecture of the cosmos. But the relentless barrage of anomalies echoing from the Large Hadron Collider and Fermilab has brought the scientific community to a terrifying and exhilarating realization. The 4 pillars are not enough. The inexplicable wobbling of the muon, the impossible mass of the W boson, and the deeply asymmetric decay of the beauty quark all point to a singular earth-shattering conclusion. There is a 5th fundamental force of nature. This is not a theoretical fantasy. It is an emerging mathematical necessity required to stop the Standard Model from completely collapsing under the weight of its own contradictory data. But if a 5th force truly exists, why has humanity remained completely blind to it for all of recorded history? The answer lies in the deeply alien nature of the quantum realm. Unlike gravity or electromagnetism, which stretch their invisible hands across millions of light years to shape the cosmos, this new 5th force operates under a completely different set of rules. It is likely confined to microscopic distances so incomprehensibly small that it can only be detected when we smash particles together at velocities approaching the speed of light. Furthermore, this hidden force is incredibly selective. It does not interact with the ordinary matter that makes up you, me, or the world around us. It is a ghost force waiting in the dark, only awakening when the heaviest and most unstable particles in the universe are violently ripped apart. But forces do not act by magic. In the strict framework of quantum mechanics, every force requires a messenger, a physical particle whose sole purpose is to carry instructions from one point in space to another. If there is a 5th force, there must be a new undiscovered force-carrying particle. Theoretical physicists are currently locked in a desperate race to identify this unseen messenger, drafting blueprints for exotic entities that challenge the very limits of human imagination. The leading candidate in this theoretical arms race is a massive hypothetical particle known as the Z-prime boson. To understand the Z-prime boson, we must look at its theoretical cousin, the Z boson, which is one of the established carriers of the weak nuclear force. The standard Z boson interacts with all particles equally respecting the sacred rule of lepton universality. But the Z prime boson is a darker, heavier, and far more chaotic entity. If it exists, the Z prime boson possesses a bizarre mathematical bias. It would interact with electrons differently than it interacts with muons. When a heavy beauty quark decays in the fiery aftermath of a collision, the Z prime boson would emerge from the quantum vacuum for a fraction of a nanosecond, heavily influencing the outcome before vanishing back into the void. This invisible interference would perfectly explain why the LHCb experiment observed beauty quarks decaying into electrons far more frequently than muons. The Z prime boson acts as a microscopic thumb on the cosmic scale, tilting the fundamental balance of nature. But as compelling as the Z prime boson is, another group of physicists is proposing an even more radical paradigm-shattering particle to explain the anomalies. They call it the leptoquark. To understand why the leptoquark is so controversial, you must understand that for 100 years particle physics has been rigidly divided into two distinct families. There are quarks, the heavy particles that build the nucleus of atoms, and there are leptons, the lighter particles like electrons and muons that orbit them. These two families are separated by an absolute impenetrable mathematical wall. A quark cannot simply transform into a lepton. The fundamental laws of classification forbid it. But the leptoquark is an unprecedented bridge particle. It is a theoretical monster that possesses the properties of both a quark and a lepton simultaneously. If leptoquarks exist, they would shatter the impenetrable wall dividing the two families of matter. They would allow quarks to directly interact with leptons, freely passing energy and identity back and forth in a microscopic dance of transformation that the standard model outright forbids. When a beauty quark shatters, a leptoquark could momentarily form in the wreckage, forcing the decay process to heavily favor the creation of electrons over muons. The existence of leptoquarks would force humanity to rewrite every single textbook on particle physics. It would mean that the distinct categories of matter we have relied upon for a century are merely an illusion, hinting at a much deeper, profound symmetry, where all matter in the universe is fundamentally connected. Whether the ghost in our machines is the biased Z prime boson, the rule-breaking leptoquark, or an entirely new class of physics we have yet to even conceptualize, one thing is absolutely certain. The age of the standard model is over. We have reached the absolute limit of the map drawn by the physicists of the 20th century. We are now sailing in uncharted, dangerous waters. The discovery of a fifth force and its corresponding particles would not just solve the anomalies of the Large Hadron Collider. It would give us a new tool, a new lens through which we can finally attempt to illuminate the darkest, most terrifying mysteries of the cosmos. Because to solve the ultimate riddle of our existence, the nature of dark matter, and the survival of the universe after the Big Bang, we must look beyond the particles we know and dive into the strangest, most elusive entities ever theorized. We must confront the invisible phantoms known as sterile neutrinos and the mind-bending possibility that our universe is bleeding energy into extra dimensions. As we desperately search for new forces and exotic particles to explain the anomalies tearing through modern physics, we must remember that this is not the first time the standard model has been broken. Long before the beauty quark decayed asymmetrically, and long before the muon wobbled out of line, there was the original ghost of the quantum realm. To find the ultimate answer to dark matter and the survival of the universe, we must look at a particle that is so elusive it borders on the supernatural. We must look at the neutrino. When the neutrino was first proposed in the 1930s by physicist Wolfgang Pauli, it was an act of pure desperation. Pauli was trying to explain missing energy in a type of radioactive decay, and to make the mathematical equations balance, he invented a microscopic thief, a particle with no electrical charge and, according to the standard model, absolutely no mass. He famously lamented that he had done a terrible thing by proposing a particle that could never be detected. For decades, the neutrino was a phantom. Because it carries no charge and supposedly no mass, it is completely immune to the electromagnetic force and the strong nuclear force. It interacts with the physical world almost exclusively through the weak nuclear force, which acts over distances smaller than an atomic nucleus. Because of this, neutrinos pass through solid matter as if it does not exist. Right now, as you breathe, trillions of neutrinos forged in the nuclear furnace of the sun are streaming through your body at nearly the speed of light. They pass through the Earth out the other side and into the infinite dark completely unimpeded. But in the late 1990s, this ghostly particle delivered the very first fatal blow to the absolute authority of the Standard Model. Deep underneath a mountain in Japan, in a massive subterranean tank of ultra-pure water known as the superconducting detector, scientists were studying neutrinos raining down from the atmosphere and the sun. The Standard Model stated that there were three distinct types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Because the Standard Model dictated that they had exactly zero mass, they should travel through space locked in their original identity forever. But the Japanese detector revealed something impossible. The neutrinos were shape-shifting. As they traveled through space, they were oscillating spontaneously, morphing from one flavor into another. In the strict laws of quantum mechanics, a particle can only experience the passage of time and therefore undergo a change or oscillation if it does not travel at the absolute speed of light. And if a particle travels slower than light, it must possess mass. The discovery of neutrino oscillation proved that neutrinos have a microscopic, almost infinitesimally small mass. It was a massive shockwave. The Standard Model was wrong. It had to be hastily patched and modified to account for this impossible weight. But while this discovery was monumental, it created a new agonizing problem. When astronomers realized that the universe was suffocating under the weight of invisible dark matter, they immediately pointed to the newly massive neutrinos. After all, they are invisible, they are everywhere, and now we knew they had mass. Could the trillions of known neutrinos drifting through space be the dark matter holding the galaxies together? The supercomputers crunched the numbers, and the answer was a devastating no. Because known neutrinos are so incredibly light and move so incredibly fast, they form what astrophysicists call hot dark matter. If the universe was held together by hot, fast-moving particles, galaxies could never have formed. The gravity of the universe requires cold, slow-moving heavy dark matter to clump together and act as the gravitational scaffolding for the stars. The three known flavors of neutrinos were too weak to save the universe. So theoretical physicists proposed a monster. They theorized a fourth generation of neutrino, a particle entirely unwritten in the Standard Model known as the sterile neutrino. The sterile neutrino is a theoretical heavyweight. It is immensely more massive than its three siblings. But what makes it truly terrifying is its isolation. The standard neutrinos at least interact with the weak nuclear force. The sterile neutrino is completely blind to it. It is entirely severed from the quantum forces of the universe. It interacts with the cosmos through one force and one force only: gravity. If sterile neutrinos exist, they would perfectly solve the ultimate mysteries of astrophysics. Because they are heavy and interact only through gravity, clouds of sterile neutrinos would pool around galaxies, providing the exact gravitational glue we observe as dark matter. Furthermore, in the chaotic first microsecond of the Big Bang, the heavy decaying sterile neutrinos could have provided the massive surge of CP violation required to destroy the antimatter and allow the normal matter of our universe to survive. They are the ultimate mathematical savior. But how do you detect a particle that only interacts through gravity? You cannot catch it in a detector. You can only look for what is missing. When the beams inside the Large Hadron Collider smash together at nearly the speed of light, supercomputers meticulously calculate the total energy of the incoming protons and compare it to the total energy of the shattering debris. The fundamental law of physics is that energy cannot be created or destroyed. The energy going in must perfectly equal the energy coming out, but occasionally the detectors register a massive, inexplicable deficit. A massive chunk of energy simply vanishes from the collision point. Where does it go? Does it fly away as an invisible sterile neutrino? Or is the truth something far more alien? The phenomenon of missing energy has breathed life into the most radical mind-bending theory in modern physics: string theory. For decades, string theorists have argued that the mathematics of our universe simply do not work in three-dimensional space. To unite the quantum world with gravity, the mathematics require the existence of at least 10 spatial dimensions. According to this theory, the reality we experience, the 3 dimensions of space and 1 dimension of time, is merely a microscopic slice of a much larger, incomprehensible multiverse. We are trapped on a dimensional membrane or a brain floating in a higher dimensional space known as the bulk. All the particles we know, the quarks, the electrons, the photons of light, are permanently glued to our 3-dimensional brain. We cannot see the extra dimensions because the very light we used to see is trapped in our dimension. But there is one force that is not trapped: gravity. In string theory, the messenger particle of gravity, the graviton, takes the form of a closed loop of string. Because it is a closed loop, it is not anchored to our dimensional brain. It can float away. It can leak into the higher dimensions. This would perfectly explain why gravity is so incredibly weak compared to the other fundamental forces. It is not weak. We are simply only feeling a fraction of its true strength, while the rest of its power leaks out into dimensions beyond human sensory perception. When the Large Hadron Collider smashes particles together and records massive amounts of missing energy, we might not just be seeing the birth of a sterile neutrino. We might be watching gravitons being blasted out of our universe. We might be watching raw energy violently punching a hole through the fabric of reality, bleeding out into a 4th, 5th, or 6th dimension. The cracks in the standard model are no longer just microscopic mathematical errors. They are the tearing of the veil. We are standing on the precipice of a scientific revolution that will fundamentally shatter our understanding of existence. The ghosts in our machines are whispering of hidden worlds of phantom forces and extra dimensions hiding just millimeters away from our eyes. But as we prepare to map this terrifying new reality, we must ask one final chilling question. What is the ultimate fate of physics, and how far is humanity willing to go to touch the face of God? For decades, theoretical physicists held on to a beautiful, elegant dream. As the cracks in the standard model began to widen, they believed they already had the perfect mathematical mortar to fix it. This dream was known as supersymmetry. Before the Large Hadron Collider ever fired its first proton, the greatest minds in physics were absolutely confident that the machine would discover a hidden, perfectly balanced mirror world of particles. Supersymmetry proposed a breathtakingly simple solution to the chaos of the quantum realm. It suggested that every single particle we know of has a heavier invisible twin, a superpartner. If these superpartners existed, they would instantly solve the deepest mysteries of the cosmos. They would provide a perfect candidate for dark matter, they would perfectly stabilize the mass of the Higgs boson, and they would restore absolute mathematical beauty to the fundamental equations of reality. It was a theory so elegant, so mathematically perfect, that physicists assumed nature simply had to utilize it. But nature, it turns out, does not care about human notions of elegance. When the Large Hadron Collider was powered up to its maximum energy, shattering protons at unprecedented velocities, the physicists waited for the superpartners to emerge from the wreckage. They waited for years. They sifted through the data of quadrillions of collisions, but the superpartners never appeared, not a single one. The devastating absence of these particles has forced the scientific community into a profound and humbling realization. We are witnessing the slow, agonizing death of supersymmetry. The failure to find these elegant solutions means that the universe is far more chaotic, asymmetrical, and unpredictable than we ever wanted to believe. We are being forced to abandon the comforting symmetry of our mathematics and face a reality that is fundamentally untidy. And this realization has triggered one of the most profound philosophical debates in the history of science. If the laws of physics are not a perfectly balanced, elegant masterpiece, we must ask a terrifying question. Are the laws of the Standard Model actually universal? For centuries, humanity operated under the assumption that the fundamental rules of nature are absolute. We believe that an electron on Earth behaves exactly the same as an electron in a galaxy 10 billion light-years away. We believed that the mass of the W boson and the strength of the weak nuclear force were fixed constants carved into the very foundation of existence. But as the anomalies multiply, a radical new perspective is taking hold among theoretical physicists. What if the physics we measure in our laboratories is not a universal law, but merely a local approximation? What if the Standard Model is just the local weather in our specific cosmic neighborhood? This brings us to the fringes of mainstream science, looking out toward the staggering concept of the quantum multiverse. String theory and advanced cosmology suggest that our universe might be just one expanding bubble in an infinite boiling ocean of universes. In this vast multiverse, the fundamental constants of nature are not fixed. They are randomized. In another universe, gravity might be billions of times stronger, instantly crushing any newly born stars into black holes. In a different universe, the electromagnetic force might be too weak to hold atoms together, leaving nothing but a sprawling, lifeless void of floating particles. But in our specific universe, the laws stabilized in a highly specific, seemingly chaotic configuration that just so happens to allow carbon to form stars to ignite and biological life to evolve. We are measuring these specific laws not because they are mathematically inevitable, but simply because we could not exist in a universe where the rules were any different. We are trapped in a fragile, localized pocket of reality. To truly understand if we are living in a multiverse or if there is a deeper unifying theory that can finally explain the anomalies, we must push beyond the limits of our current technology. The Large Hadron Collider has been a magnificent machine. It found the Higgs boson and it exposed the first fatal cracks in the Standard Model. But it has reached the absolute limit of its power. The ghosts hiding in the quantum vacuum are too heavy, too elusive, and too energetic for the current machine to catch. To capture the particles responsible for dark matter, to isolate the fifth fundamental force, and to finally chart the dark sectors of the universe, humanity must build a new cathedral of science. We must build the ultimate time machine. Deep within the planning rooms of CERN, the blueprints have already been drawn for the next great leap in human engineering. It is called the Future Circular Collider, or the FCC. If approved and funded, it will dwarf the Large Hadron Collider in every conceivable metric. The current collider is 27 kilometers around. The Future Circular Collider will be a staggering 100 kilometers in circumference. It will require excavating a massive circular tunnel that stretches entirely beneath the city of Geneva, passing under Lake Geneva, and carving deep into the bedrock of the French Alps. To power this leviathan, engineers will have to develop an entirely new generation of superconducting magnets capable of generating fields so intense they push the very limits of material science. The machine will smash particles together with an energy output at least 7 times greater than the current collider, creating microscopic fireballs that perfectly mimic the state of the universe, just fractions of a nanosecond closer to the absolute moment of creation. But this unprecedented ambition comes at a staggering cost. The estimated price tag for the Future Circular Collider is $20 billion. And the timeline for its construction is even more daunting. Even if the global scientific community and international governments aligned to fund the project today, the tunnel would not be completed until the mid-2040s, and the machine would not begin its highest energy collisions until the 2070s. We are talking about a project so massive, so technologically demanding, that the brilliant physicists drafting its blueprints today know they will likely not live to see it completed. They are designing a machine for their students and for their students' students. It is a multi-generational commitment to the pursuit of truth. Why do we do it? Why invest billions of dollars and decades of human life to chase invisible ghosts in the quantum void? Because the alternative is to stop. The alternative is to accept a broken map, to look up at the stars and admit that we will never understand 95% of the cosmos. Humanity has never accepted ignorance. From the moment we looked up at the night sky and wondered what the stars were made of, we have been driven by an insatiable, relentless need to understand our place in the universe. The anomalies we have discovered are not the end of physics. They are the beginning of a terrifying, magnificent new chapter. The fortress of the Standard Model is crumbling, but from its ruins a new understanding of reality will eventually rise. We are building the machines that will one day pull back the final veil, revealing the true chaotic and unimaginably beautiful architecture of the cosmos. I always believed that the most terrifying aspect of the cosmos was the sheer suffocating emptiness between the stars. But the reality physicists are currently uncovering is infinitely more chilling. When you step outside on a clear, cold night and gaze up at the sprawling architecture of the Milky Way, you are falling victim to the greatest optical illusion in human history. You might think you're looking at the universe in all its majestic glory. You are not. Every single glowing star, every swirling nebula, every planet and every biological organism on Earth combined makes up a pathetic 5% of the actual cosmos. The overwhelming majority of the universe is completely invisible, untouchable, and utterly silent. We call it dark matter. It is the invisible scaffolding of reality, the phantom gravity that holds our galaxy together and prevents the stars from violently flinging themselves out into the freezing intergalactic void. For decades, humanity proudly believed that our science had illuminated the darkest corners of creation. We mapped the cosmic microwave background, we split the atom, and we walked on the moon. And yet 85% of the gravitational force binding our very own galaxy is being generated by a ghost. To understand the sheer desperation of modern physics, we have to understand the catastrophic failure of the Great Underground Hunt. For the last 40 years, the brightest minds on the planet were absolutely convinced that dark matter was simply a new, undiscovered type of subatomic particle. They called them WIMPs, or weakly interacting massive particles. The theory was beautiful, elegant, and mathematically perfect. It suggested that trillions of these microscopic phantom particles were passing through your body, through the walls of your house, and through the core of the Earth every single second completely undetected. To catch these elusive ghosts, scientists embarked on one of the most ambitious and expensive engineering crusades in history. They retreated deep underground, beneath the towering peaks of the Gran Sasso Mountain in Italy, and buried miles down inside abandoned gold mines in South Dakota. They built heavily fortified subterranean laboratories. They had to go this deep to shield their incredibly sensitive instruments from the relentless bombardment of cosmic rays raining down from the sun. Inside these deep earth bunkers, they constructed massive pristine tanks filled with ultra-pure liquid xenon, cooled to freezing temperatures. The plan was incredibly simple yet breathtakingly precise. They would sit in the dark, watching the liquid xenon, hoping that just one single WIMP out of the trillions passing through the Earth would accidentally crash into a xenon atom and produce a microscopic flash of light. We built the most sensitive radiation detectors in the history of human civilization, and we waited in the silent depths of the Earth. We waited for years. Years slowly turned into decades. We continuously upgraded the machines, making them larger, colder, and exponentially more sensitive. We meticulously filtered out every conceivable source of background noise until the xenon tanks were the quietest, most undisturbed places in the solar system. And we continued to wait, but the flash of light never came. The Great Underground Hunt was a catastrophic failure. Millions of dollars and the entire careers of brilliant physicists were swallowed by a deafening, unrelenting silence. The data from the most advanced detectors on Earth returned absolutely nothing. The WIMP theory, the beautiful mathematical dream that had sustained the physics community for half a century, was slowly bleeding to death. We assumed that the missing mass of the universe had to be a microscopic particle. We spent 40 years digging into the earth to find it, and we found absolutely nothing. But as the underground detectors failed, a profound and terrifying realization began to ripple through the scientific community. What if our fundamental assumption was entirely wrong? What if dark matter is not a new exotic subatomic particle at all? What if it is not something microscopic that we need to catch in a vat of liquid xenon? Therefore, in a desperate bid to save our understanding of reality, theoretical physicists are now abandoning the particle hunt and returning to a radical, almost heretical idea first proposed by Stephen Hawking and Yakov Zeldovich in the 1970s. They are looking away from the subatomic quantum world and turning their gaze toward the most violent, destructive, and ancient entities ever forged by the cosmos. They are hunting for the ultimate cosmic predator. If dark matter is not a particle, then the only other mathematical candidate capable of generating that much invisible phantom gravity is a black hole. But not the type of black hole you're thinking of. When you hear the word black hole, you instinctively imagine a dying star. You imagine a massive sun, millions of times larger than our own, running out of nuclear fuel, collapsing under its own crushing weight, and detonating in a spectacular supernova, leaving behind a singularity that devours everything in its gravitational path. Those are stellar mass black holes. They are terrifying, but they are relatively young. They could only be born after the first generations of stars ignited, lived their lives and died. But the dark matter we observe in the universe has been there since the very beginning, acting as the gravitational seeds that pulled the first galaxies together. Stellar mass black holes cannot be dark matter because they simply did not exist early enough in the timeline of the universe to do the heavy lifting of galaxy formation. This is where the story shifts from the massive to the microscopic, and from the end of a star's life to the very first fraction of a second of time itself. Long before there were stars to collapse, long before there were galaxies, and long before the universe was anything more than a blindingly hot, chaotic soup of pure energy, a different breed of monster was born. We are talking about primordial black holes. These are not the corpses of dead stars. These are the fossilized scars of the Big Bang itself. They were forged in a time when the universe was so dense, so incredibly hot, and so violent that the very laws of physics were completely unrecognizable. The answer to the greatest mystery of the cosmos might not be a gentle particle floating through the dark, but a swarm of ancient invisible singularities that have been silently stalking the universe for 13.8 billion years. And to understand how these primordial monsters were born, we have to travel back to the first microsecond of creation, to a moment when the universe was a terrifying boiling crucible of infinite pressure. To truly grasp the magnitude of what a primordial black hole is, you must completely discard everything you have ever been taught about how gravity works in the modern universe. Today, if you want to create a black hole, you need the mass of at least 3 suns to force matter to collapse against the powerful outward pressure of nuclear fusion and quantum mechanics. The modern universe is simply too cold and too empty to create a singularity any other way. But the first instant of the Big Bang was a completely different realm. The universe was not empty. It was compressed into a space smaller than a single atom containing all the energy that will ever exist. It was an environment of absolute unimaginable extremes. In that primordial furnace, you did not need a dying star to create a black hole. You only needed a microscopic imperfection. You only needed a tiny, fleeting quantum fluctuation. We are about to realize that the dark space between the stars is not empty at all. It is heavily populated by the silent remnants of the very first second of time. These ancient entities have survived the birth of the cosmos, they have outlived the formation of our solar system, and they will undoubtedly outlive humanity. They hold the key to understanding not just the missing mass of our galaxy, but the ultimate fate of the entire universe. As we peel back the layers of this cosmic mystery, we must prepare ourselves for a paradigm shift that will shatter our fundamental understanding of reality. The hunt for dark matter has completely transformed from a quiet search for microscopic particles into a terrifying realization that we are surrounded by ancient invisible gravity wells. Every textbook, every classroom, and every popular science documentary has taught you the exact same story about how a black hole is born. You have been told that to create a black hole you must first have a star. A massive ancient star, burning millions of times brighter than our sun, running out of nuclear fuel, collapsing under its own crushing gravity, and detonating in a brilliant supernova. But what if I told you that the most dangerous black holes in the universe did not require a star at all? What if I told you there are black holes currently drifting through our galaxy that were born in complete darkness long before the universe ever had its first beam of light? To find these ancient monsters, we cannot look at dying stars. We must look at the very beginning of everything. We must travel back in time, past the formation of the Earth, past the ignition of the very first suns, and plunge directly into the violent, blinding crucible of the Big Bang. We are going back to the first fraction of a single second of creation. Most people imagine the Big Bang as a perfect smooth explosion, like a balloon inflating flawlessly in all directions, a perfect sphere of expanding energy. But the universe has never been perfect. It has always been chaotic, governed by the unpredictable, jittery laws of quantum mechanics. In the realm of the incredibly small, energy and matter are not static. They are constantly bubbling, shifting, and fluctuating in a boiling quantum sea. This microscopic chaos is known as a quantum fluctuation. Now imagine taking this microscopic chaotic bubbling and stretching it across the entire cosmos in an instant. During the first billionth of a trillionth of a second after the Big Bang, the universe underwent a period of terrifyingly rapid expansion known as cosmic inflation. As space expanded faster than the speed of light, it took those tiny microscopic quantum ripples and froze them into the very fabric of the cosmos. Because of these frozen ripples, the early universe was not a smooth, even plasma. It was incredibly lumpy. There were regions of space where the primordial soup of energy and subatomic particles was slightly less dense, and there were regions where it was unimaginably overwhelmingly dense. I want you to try and comprehend the physical conditions of the universe during this specific microsecond. The temperature was measured not in degrees, but in trillions of degrees. It was a heat so absolute that atoms could not even form. The universe was a boiling plasma of pure quarks and gluons, and the pressure was beyond human comprehension. In those localized hyperdense regions created by the quantum fluctuations, the mass was packed so tightly together that gravity began to assert its ultimate undeniable dominance. In the modern universe, when a massive cloud of matter collapses, it forms a star, and the outward pressure of nuclear fusion halts the gravitational collapse. But in the first microsecond of the Big Bang, there were no atoms to fuse. There was no light to push back against the crushing weight. There was only raw, unadulterated mass and the inescapable tightening grip of gravity. And the pressure was so immense, so terrifyingly concentrated, that the matter simply gave up. It did not ignite into a star. It did not form a swirling gas cloud. It collapsed directly into itself, tearing a microscopic hole in the fabric of space-time. Let us pause for a moment to truly understand what a singularity actually is, especially one born in the chaotic fires of the Big Bang. A singularity is not a physical object in the way a planet or a star is an object. It is a mathematical nightmare. It is a point in space where matter has been crushed down to zero volume, causing the density to reach absolute infinity. In the modern era, creating infinite density requires the agonizing death of a supergiant star to overcome the fundamental forces of nature. But in the primordial universe, the entire cosmos was already hovering on the razor-thin edge of infinite density. The quantum fluctuations were simply the gentle nudge that pushed those localized regions over the edge into oblivion. It was an epic of violent, spontaneous creation. As the universe rapidly expanded, the overall density of the surrounding plasma began to drop. This rapid cooling meant that the window of opportunity to create these primordial black holes was incredibly short. It lasted for only a microscopic fraction of a single second, but in that infinitesimally brief window, an unimaginable number of singularities were violently forged. Think of bubbles forming rapidly in a pot of boiling water, but instead of empty pockets of air, these were pockets of infinite gravity. In an instant, billions upon billions of these hyper-dense pockets crushed themselves out of existence, leaving behind only their gravitational footprint. They were born in a swarm, a cosmic plague of microscopic gravity wells popping into existence throughout the expanding plasma. Unlike stellar black holes, which are strictly restricted in size by the physics of dying stars, these primordial entities had absolutely no such limits. The size of a primordial black hole was dictated purely by the size of the quantum fluctuation that birthed it. Some were incredibly small, formed from tiny ripples of overdensity. Others were monstrous, forged in massive gravitational vortexes. They were the very first definitive structures to ever exist. They predated the first atoms. They predated the cosmic microwave background. They are quite literally older than light itself. When the universe finally cooled enough to allow light to travel freely, when the blinding fog of plasma lifted and space became transparent, these ancient monsters were already there waiting in the dark. As space continued to stretch and cool, dragging the newly formed matter along with it, these primordial black holes were swept up in the cosmic tide. They watched silently as the first clouds of hydrogen coalesced. They watched as the very first stars ignited and bathed the universe in fresh light. They watched as those stars died and birthed the spiraling galaxies. And they watched as our solar system formed from the swirling dust. For 13.8 billion years, they have been wandering the cosmos. They are the ultimate living fossils of the Big Bang. They carry within them the frozen, crushed imprint of the exact moment of creation. While everything else in the universe has evolved, decayed, exploded, or transformed, these primordial black holes have remained exactly as they were in the first microsecond of time. And because they do not emit light, because they do not reflect light, and because they do not interact with normal matter, except through their devastating gravitational pull, they are completely invisible to our telescopes. They have been hiding in plain sight, scattered across the vast dark halos of every galaxy in the universe, including our own Milky Way. We have spent decades looking up at the stars, trying to find the missing mass that holds our world together, completely unaware that we are swimming in an ancient ocean of invisible wandering singularities. And the most terrifying part is not that they exist. The most terrifying part is how incredibly small and how incredibly close to us they might actually be. If a rogue black hole entered our solar system right now, you would probably assume it would be a catastrophic world-ending event. I always thought a wandering black hole had to be a colossal planet, devouring behemoth that would swallow the sun and plunge the Earth into an eternity of absolute darkness. But the reality physicists are now uncovering is vastly more unsettling and entirely counterintuitive. The black hole currently drifting through our cosmic neighborhood might not be the size of a gas giant or even the size of a small moon. It might actually be no larger than a standard ping-pong ball. To understand how something so devastating can be so incredibly small, we have to completely dismantle everything you think you know about the size and weight of these cosmic monsters. We have to look at the terrifying mathematics of extreme compression. When we look out into the modern universe, we only see two types of black holes. We see stellar mass black holes, which are born from the violent deaths of giant stars and are typically a few dozen miles across. And we see the supermassive black holes lurking at the centers of galaxies, like Sagittarius A star, which are millions or even billions of times heavier than our Sun and can span distances larger than our entire solar system. Because these are the only types we can actively detect, we have been culturally conditioned to believe that black holes must be exceptionally large. But the laws of physics disagree. According to Albert Einstein's theory of general relativity, any object, literally anything in the universe, can become a black hole if you compress it tightly enough. This boundary of compression is mathematically defined as the Schwarzschild radius. every single object with mass has one. If you were to take the Earth with all its oceans, continents, and a core of molten iron, and somehow compress all of that mass down to the size of a peanut, the gravitational pull at its surface would become so overwhelmingly intense that light itself could not escape. The Earth would instantly become a black hole. If you wanted to turn the Moon into a black hole, you would have to crush it down to the size of a single grain of sand. In the cold, expansive environment of the modern universe, there is no natural mechanism capable of exerting that kind of microscopic pinpoint pressure. Stars can only compress matter down to a certain limit before the laws of quantum mechanics push back. But as we discovered in the first microsecond of the Big Bang, the early universe was a realm of infinite pressure. The primordial black holes forged in those chaotic quantum fluctuations were not limited by the mass of a dying star. They were limited only by the size of the localized density spikes that birthed them. Therefore, primordial black holes can exist at practically any mass and any size imaginable. They shatter our conventional understanding of scale. A primordial black hole could have been formed with the exact mass of the planet Jupiter, but compressed into a sphere no larger than an apple. More terrifyingly, they could be significantly smaller. Consider Mount Everest, the largest, heaviest mountain on Earth, composed of billions of tons of solid rock and ice. In the fiery crucible of the early cosmos, a primordial black hole could have been forged with the exact same mass as Mount Everest, but crushed down to a physical size smaller than a single proton. The weight of a mountain compressed into an entity smaller than an atom. If you want to solve the mystery of dark matter, this mind-bending distortion of size and mass is exactly what you need. Astronomers know that the dark matter holding the Milky Way together is not concentrated in the galactic disk where the stars are. Instead, it forms a massive, invisible spherical halo that engulfs the entire galaxy, extending hundreds of thousands of light-years out into the empty intergalactic void. If this halo were made of giant stellar mass black holes, we would have seen their gravitational effects by now. They would be violently disrupting the orbits of visible stars, shredding solar systems apart, and creating massive glowing accretion disks as they devoured interstellar gas. But we do not see that chaotic destruction. The dark matter halo is silent. This absolute silence perfectly aligns with the existence of microscopic primordial black holes. Imagine a swarm not of giant cosmic vacuum cleaners, but of trillions upon trillions of these subatomic mountain mass singularities drifting through the galactic halo. Because their physical size is microscopic, their event horizons, the point of no return where light is trapped, are incredibly tiny. An atom-sized black hole does not have a gravitational reach large enough to swallow a star, or even a planet from a distance. If an asteroid-sized primordial black hole carrying the mass of the Earth were drifting through our solar system, you would not even notice its gravitational pull until it was practically right on top of you. But what would actually happen if one of these ancient invisible ghosts directly intersected with our planet? The scenario is the stuff of pure science fiction nightmares, but mathematically, it is entirely possible. If a primordial black hole the mass of Mount Everest and the size of an atom struck the Earth, it would not shatter the planet in a spectacular explosion. Its physical cross-section is so infinitesimally small that it would pass straight through the solid rock, the boiling mantle, and the molten iron core, as if the Earth were made of empty space. It would enter the atmosphere at extreme velocities, pierce the crust like a microscopic invisible needle, and exit the other side of the planet in a matter of minutes. The only evidence of its passage would be a microscopic superheated tunnel left in its wake, and perhaps a highly localized, inexplicable seismic tremor. It would act exactly like the dark matter we observe passing completely through normal matter without interacting, leaving behind only the faintest gravitational footprint. For decades, the greatest minds in physics have been searching for an elusive invisible cloud of subatomic particles to explain the missing mass of the universe. They built massive underground bunkers and filled them with freezing liquid xenon, hoping to catch a single WIMP. But they were looking for the wrong kind of ghost. The gravitational web that holds the Milky Way together, the invisible scaffolding that gave birth to the first stars and allowed humanity to exist, might not be a cloud of gentle particles. It is likely a swarm of ancient hyper-dense predators, trillions of microscopic singularities forged in the absolute dawn of time, silently swimming through the dark void between the stars. We are not just drifting through empty space. We are sailing through a vast invisible ocean of atom-sized black holes. And as we continue to map the heavens, we are beginning to realize that these primordial ghosts are not completely immortal. Because as Stephen Hawking famously discovered, even a black hole can bleed. If a primordial black hole is perfectly invisible, and if its gravitational reach is so incredibly microscopic that it could pass straight through the Earth without us even noticing, how could humanity ever hope to prove that they actually exist? You might assume that these ancient singularities are completely immortal, silent phantoms forever trapped behind their event horizons, completely severed from the world of light. But you would be fundamentally wrong. The key to hunting down these ancient monsters does not come from observing their gravity, but from understanding their ultimate terrifying death. And this profound revelation came from the brilliant mind of theoretical physicist Stephen Hawking. To understand how a black hole dies, we must first shatter the oldest and most stubborn myth in astrophysics. For decades, scientists believed that a black hole was the ultimate cosmic roach motel, a perfect one-way street where matter and light could check in, but absolutely nothing could ever check out. According to Albert Einstein's classical theory of general relativity, once an object crosses the event horizon, the gravitational pull becomes infinite, and escape requires a velocity greater than the speed of light, which is physically impossible. Therefore, a black hole should be entirely perfectly black. It should last forever, growing slowly as it consumes interstellar dust, but never giving anything back to the universe. But in the 1970s, Stephen Hawking realized that this classical picture was incomplete. He understood that to discover the true nature of a black hole, you cannot just look at gravity. You must combine the crushing macroscopic forces of general relativity with the microscopic chaotic laws of quantum mechanics. Hawking turned his mathematical focus to the razor-thin boundary of the event horizon itself. As we established earlier in the realm of quantum mechanics, empty space is never truly empty. It is a boiling turbulent sea where pairs of virtual particles, a particle and an antiparticle, are constantly popping into existence, borrowing energy from the universe, and then instantly colliding and annihilating each other back into nothingness. This happens everywhere all the time, completely unnoticed by the macroscopic world. But what happens if one of these virtual particle pairs spontaneously materializes exactly on the microscopic edge of a black hole's event horizon? The environment there is so gravitationally extreme that it rips the pair apart before they have a chance to annihilate. One particle is sucked across the event horizon and falls into the singularity, while its partner is violently flung outward, escaping into deep space. To the rest of the universe, this escaping particle is no longer virtual. It has become a real particle carrying away a tiny fraction of actual energy. Because the universe demands absolute balance and energy cannot be created from nothing, the energy required to make that escaping particle real must be stolen directly from the mass of the black hole itself. This means the black hole is leaking. It is radiating heat. It is slowly, agonizingly bleeding its mass away into the cold void of space. This phenomenon is known as Hawking radiation. Black holes are not entirely black, and they are absolutely not immortal. They evaporate. But the mathematics of Hawking radiation dictate a deeply counterintuitive rule. The rate at which a black hole evaporates is completely inverted relative to its physical size. The larger and heavier a black hole is, the colder it is and the slower it leaks. The supermassive black holes at the centers of galaxies are so unfathomably huge that their temperature is a fraction of a degree above absolute zero. They are colder than the empty space around them, meaning they are currently absorbing more background radiation than they emit. They will take hundreds of trillions of years to even begin to significantly evaporate. Even a standard stellar mass black hole born from a dying star will outlive the last shining stars in the universe by an incomprehensible margin. But primordial black holes are fundamentally different. As we discovered, a primordial black hole can be incredibly small. It can be the mass of a mountain compressed into the size of a single proton. And because it is so incredibly small, its surface temperature is searingly hot. A microscopic black hole is not sitting silently in the dark. It is actively boiling away. It is fiercely pumping radiation out into the cosmos, losing its mass at an ever-accelerating rate. This evaporation creates a terrifying runaway feedback loop. As the primordial black hole radiates energy, it loses mass. As it loses mass, its physical size shrinks. As it shrinks, its temperature skyrockets. And as its temperature skyrockets, it radiates energy even faster. It is a cosmic death spiral that stretches over billions of years, slowly accelerating until the final apocalyptic climax. When the primordial black hole finally shrinks down to the absolute quantum limit, it does not simply wink out of existence, it detonates. In the final fraction of a second of its life, the evaporation rate approaches infinity. The black hole violently unleashes all of its remaining mass energy in a single catastrophic explosion. It erupts with the force of billions of nuclear weapons, sending a blinding concentrated flash of high-energy gamma rays screaming across the universe. This is the exact moment humanity is desperately trying to catch. When we calculate the mathematics of Hawking radiation, we discover a chilling coincidence. If a primordial black hole was forged in the Big Bang with roughly the mass of a large asteroid, a few billion tons of matter, its total evaporation lifespan would be approximately 13.8 billion years. That is exactly the current age of our universe. This implies that right now, hidden in the dark matter halo of the Milky Way galaxy, an entire generation of ancient asteroid mass primordial black holes are reaching the very end of their lifespans. They are actively detonating. Astronomers are currently pointing our most advanced space-based telescopes, like the Fermi Gamma Ray Space Telescope, into the deep empty voids of the galactic halo. They are not looking for the continuous glow of stars. They are hunting for highly specific, isolated, and incredibly violent flashes of gamma radiation that cannot be explained by supernovas or collapsing stars. They are searching for the dying screams of the Big Bang's earliest children. If we can capture just one of these distinct gamma ray signatures, it would instantly prove the existence of primordial black holes. It would validate Stephen Hawking's most profound theory, and it would revolutionize our entire understanding of dark matter. It would prove that the missing mass of the universe is not a swarm of microscopic particles, but a vast boiling ocean of decaying singularities. The universe is not a static, silent graveyard. It is a highly active, violent crucible. These invisible gravity wells, the very entities that acted as the gravitational seeds for our galaxies, are slowly burning themselves away in the dark. We are surrounded by billions of ticking time bombs waiting to release their ancient primordial energy back into the cosmos. But even as we search the skies for these blinding flashes of light, another instrument back on Earth has already detected something far more profound. They have not seen a primordial black hole explode. They might have actually heard them collide, and the sound they captured shook the very fabric of space-time itself. I used to think that the idea of ancient invisible black holes drifting through our galaxy was just a mathematical fantasy that would forever remain trapped on the chalkboards of theoretical physicists. For decades, it seemed entirely impossible to prove their existence, because human astronomy has always suffered from one fundamental crippling limitation. Since the dawn of civilization, when our ancestors first looked up at the night sky, we have been entirely dependent on light. Every telescope we have ever built, from the glass lenses of Galileo to the massive golden mirrors of the James Webb Space Telescope, relies on capturing some form of electromagnetic radiation. We look for visible light, infrared, ultraviolet, X-rays, and radio waves. But primordial black holes do not emit any of these. They are completely dark and completely silent in the electromagnetic spectrum. If you want to find a monster that is perfectly invisible to light, you cannot use a telescope. You have to build a machine that can actually feel the fabric of reality vibrating. You have to learn how to listen to the universe. In 1916, Albert Einstein predicted that space and time were not an empty static stage where the events of the universe play out. He proposed that space-time is a flexible dynamic fabric that can be warped and stretched by mass. He theorized that when two incredibly massive objects like black holes orbit each other at extreme velocities, they should violently churn this fabric, creating invisible ripples of gravity that radiate outward at the speed of light. These are gravitational waves. For a century, they remained a purely theoretical concept because gravity is by far the weakest of the four fundamental forces. By the time a gravitational wave from a distant galaxy reaches the Earth, the stretching and squeezing of space-time is so infinitesimally small that it is equivalent to measuring the distance from our planet to the nearest star Proxima Centauri with an accuracy of a single human hair. Most physicists believed we would never possess the technology capable of detecting something so microscopically faint, but humanity refused to accept that limitation. We built the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO is not a telescope. It is a monumental masterpiece of extreme engineering. It consists of massive L-shaped vacuum tubes stretching for miles across the American landscape. Inside these tubes, scientists fire highly stabilized laser beams, bouncing them back and forth between the most perfectly polished mirrors ever created, suspended by microscopic glass threads to isolate them from the seismic vibrations of the Earth. The machine is designed to detect a change in the length of those miles-long tubes that is 10,000 times smaller than the nucleus of a single atom. It is arguably the most sensitive measuring device ever constructed in the history of our species. On September 14, 2015, the silence of the cosmos was finally broken. The LIGO detectors in Washington and Louisiana simultaneously registered a microscopic anomaly. The laser beams shifted by a fraction of an atomic nucleus. The Earth had literally stretched and squeezed. When supercomputers translated this microscopic physical distortion into an audio frequency, the scientists heard a distinct ascending tone. It was a cosmic chirp. It was the sound of two massive black holes locked in a desperate death spiral, colliding and merging into a single entity. The impact was so unfathomably violent that for a fraction of a second, the collision radiated more power into the universe than all the shining stars in all the observable galaxies combined. But this energy was not light. It was pure, unadulterated gravity. The scientific community erupted in celebration. We had finally proven Einstein's century-old prediction. But as astrophysicists began to dissect the data from that first collision and the dozens of collisions that were detected in the following years, the initial euphoric celebration slowly morphed into a profound, chilling confusion. The data was revealing something deeply anomalous about the black holes that were crashing into each other. The anomaly was rooted in their mass. According to the standard models of stellar evolution, we know exactly how heavy a black hole should be when a star dies. When a massive star exhausts its nuclear fuel and its core collapses, it typically creates a black hole weighing roughly 5 to 20 times the mass of our Sun. However, if a star is too massive, it undergoes a phenomenon known as a pair instability supernova. In this apocalyptic scenario, the core becomes so intensely hot that it spontaneously generates pairs of electrons and antimatter positrons, causing a catastrophic drop in internal pressure. The star violently detonates, completely obliterating itself and leaving absolutely nothing behind, not even a black hole. Because of this absolute physical limit, astronomers mathematically established a strict forbidden zone known as the mass gap. The laws of stellar physics dictate that there should be absolutely no black holes existing anywhere in the universe, with a mass between roughly 50 and 130 times the mass of our Sun. Stars simply cannot produce them. They are mathematically forbidden. But LIGO was not listening to mathematical theories. It was listening to reality, and the reality was terrifying. In September 2020, the LIGO collaboration announced the detection of an event designated as GW190521. It was the heaviest black hole collision ever observed at that time. When they calculated the masses of the two spiraling monsters, they realized that one of them weighed roughly 85 times the mass of our Sun, and the other weighed about 66 times the mass of our Sun. They were both sitting squarely inside the forbidden mass gap. They were too heavy to have been born from a collapsing star. By all the known laws of astrophysics, they simply should not exist. Astrophysicists scrambled to find an explanation. Some suggested that perhaps these impossible objects were the result of previous multiple mergers where smaller black holes collided and slowly grew over billions of years. But the statistical probability of such successive mergers happening frequently enough to explain the LIGO data in the vast empty expanse of space is incredibly low. As more and more anomalous masses were detected in subsequent runs of the LIGO detectors, a much older, much darker theory began to rise from the ashes. What if these massive colliding objects were not the corpses of dead stars at all? What if LIGO was actually hearing the ancient echoes of the Big Bang? If you recall the fiery, chaotic crucible of the first microsecond of the universe, you will remember that primordial black holes are not bound by the strict rules of stellar evolution. They are not limited by the physics of nuclear fusion or pair instability supernovas. They were forged purely by the random fluctuations of the quantum vacuum. A primordial black hole can easily be born with a mass of 85 suns. It can be born with a mass of 30 suns. It can exist perfectly within the forbidden mass gap because it was created long before those astronomical rules were ever written. The implications of this realization are absolutely staggering. The anomalous gravitational waves washing over our planet might be the definitive smoking gun proving the existence of primordial black holes. We might be listening to the dense invisible clusters of dark matter interacting in the deep halos of distant galaxies. When these ancient singularities drift too close to one another in the freezing dark, their immense gravitational fields lock them into an inescapable spiral. They dance for billions of years, slowly bleeding energy into the fabric of space-time until they finally violently crash together, sending a ripple across the universe that eventually rings the bells of our detectors on Earth. We have officially entered a completely new era of science. We are no longer deaf to the cosmos. We have built mechanical ears that can hear the silent collisions of invisible monsters in the dark. The discovery of these forbidden masses has violently reopened the debate on dark matter, forcing the scientific community to accept that our galaxy might be teeming with primordial singularities. But as we look toward the inevitable future of the cosmos, we realize that these ancient entities are not just relics of the past. They are the ultimate inheritors of reality. Long after the stars burn out and the galaxies fade into eternal darkness, the primordial black holes will be the only things left standing. Every time we look up at the night sky, we are witnessing a temporary fragile spark of light in an ocean of eternal darkness. We take the warmth of the sun and the glowing tapestry of the Milky Way for granted, assuming that the universe will always be a vibrant, bustling theater of cosmic evolution. But the terrifying truth of astrophysics is that the era of starlight is merely a fleeting microscopic chapter in the grand timeline of reality. The universe is not a perpetual motion machine. It is slowly running out of fuel. And to truly understand the profound significance of primordial black holes, we must follow them out of the chaotic fires of the Big Bang, out of the galactic halos, and march relentlessly forward into the darkest, most terrifying epoch of the far future. We must travel to the absolute end of time. Right now, we are living in what astrophysicists call the stelliferous era. This is the age of stars. It is an era characterized by the continuous ignition of hydrogen gas forming brilliant galaxies that illuminate the expanding cosmos. But this era is mathematically doomed to end. In roughly 100 trillion years, the last clouds of interstellar gas will be completely exhausted. The universe will permanently lose the ability to forge new stars. The massive brilliant blue giants have already burned through their fuel and died long ago. Eventually, even the most conservative red dwarf stars, the longest living engines in the cosmos, will slowly fade into cold dead embers known as black dwarfs. The galaxies will gradually go dark. The universe will be plunged into an era of eternal night. This is the beginning of the degenerate era. It is a time when the cosmos is populated only by the frozen corpses of planets, dead black dwarf stars, and wandering neutron stars. But the true rulers of this freezing barren wasteland will be the entities that have been waiting in the dark since the very first microsecond of creation. The black holes. As the universe continues to expand at an ever-accelerating rate, driven by the relentless repulsive force of dark energy, the dead galaxies will be violently ripped apart. The space between objects will stretch so vast that the night sky of any surviving planet would be absolutely pitch black, completely devoid of neighboring stars or distant galaxies. In this terrifyingly empty void, the primordial black holes will finally emerge from the shadows. Throughout the age of stars, these microscopic mountain mass singularities were hidden, masked by the overwhelming brilliance of stellar fusion and the chaotic gravitational dances of massive planets. But in the degenerate era, they are the undisputed masters of reality. For billions upon billions of years, they will silently wander the freezing void, occasionally colliding and merging, sending silent gravitational screams across a dead universe. But as we established earlier, even these ultimate cosmic predators are not immortal. They are bleeding. As the universe grows colder and colder, the Hawking radiation leaking from their event horizons begins to accelerate. Before the black hole era truly takes hold, another catastrophic event might seal the fate of the physical world. Theoretical physics suggests that protons, the very building blocks of atomic nuclei, are not stable forever. Over unimaginable timescales, perhaps 10 to the power of 34 years, protons themselves may spontaneously decay into lighter subatomic particles and radiation. If proton decay is a reality, then long before the supermassive black holes evaporate, every single remaining planet, every dead star, and every frozen asteroid will simply dissolve into a mist of glowing radiation. The solid matter that makes up everything we know will be fundamentally erased from existence. In this apocalyptic scenario, the only structured objects left in the entire cosmos will be the singularities. They will be the ultimate and sole inheritors of reality, the uncontested rulers of a decaying void. We are entering the black hole era. To comprehend the time scale of this epoch, you must completely abandon the human concept of time. We are no longer talking about billions or trillions of years. We are talking about years numbered by a 1 followed by 100 zeros, a Google of years. During this incomprehensible stretch of eternity, the supermassive black holes that once anchored the centers of galaxies will slowly agonizingly boil away into the vacuum. But the primordial black holes, because of their significantly smaller mass, will be the first to reach their explosive climax. Imagine a universe that has been pitch black for trillions of years. No warmth, no light, no physical structure. The temperature is a microscopic fraction above absolute zero. And then suddenly, in the freezing dark, a blinding flash of gamma radiation violently erupts. A primordial black hole has finally reached the quantum limit and detonated. For a fleeting instant, the dead universe is illuminated by the dying scream of an entity that was originally forged in the Big Bang. Millions of years later, in another corner of the empty void, another flash, and then another. Like solitary fireworks in a vast empty stadium, the primordial black holes will provide the final fading light show of the cosmos. When the last black hole finally evaporates, the universe will officially enter the dark era. All complex matter will have decayed. The cosmos will be a sprawling infinite void filled with nothing but a thin freezing mist of photons and subatomic particles drifting further and further apart. Nothing will ever happen again. Time itself will essentially lose all meaning because there will be no events left to measure it. The universe will have reached its final state of maximum entropy, the ultimate thermodynamic death. This is the staggering legacy of the primordial black holes. They are the Alpha and the Omega. They are the only entities in existence that bridge the terrifying extremes of our reality. They were born in the blinding, infinite heat of the first microsecond of the Big Bang, acting as the gravitational seeds that pulled the dark matter halos together and allowed the first galaxies to form. They held the universe together when it was young, providing the necessary scaffolding for the stars to ignite and for biological life to evolve. And they will be the last surviving monuments of the cosmos, acting as the final flickering lights before the universe descends into an eternity of absolute freezing darkness. We spent 40 years digging deep into the Earth, desperately searching for a microscopic particle to explain the missing mass of our galaxy. We assumed the universe was built on a foundation of gentle, invisible dust. But the truth is infinitely more violent and infinitely more poetic. The missing mass, the phantom gravity that shapes our world, is likely a swarm of ancient microscopic singularities. We are surrounded by ghosts, and as we continue to build more sensitive gravitational wave detectors and point our gamma-ray telescopes into the deepest voids, we are finally beginning to map their invisible empire. We are finally learning to listen to the silent whispers of the Big Bang. But if the universe is destined to end in a freezing empty void where nothing can ever exist again, what is the point of it all? Is our universe merely a solitary doomed bubble floating in an endless abyss? The anomalies we have discovered, the ghosts we have chased, suggest that our reality is far more complex than a simple single timeline. In the next video, we are going to leave the three-dimensional confines of our dying universe and step out into the terrifying mind-bending architecture of the multiverse. We will explore string theory, the hidden 10 dimensions of reality, and the mathematical possibility that our universe is just one microscopic, vibrating membrane in an infinite ocean of parallel worlds. You do not want to miss the truth about the dimensional cage we are living in. Make sure to subscribe to the channel and turn on notifications, because next week we are going to completely shatter your understanding of existence. See you in the higher dimensions.